Let's look at two simple tests for extreme points. The first one takes advantage of the first derivative, and it's really about looking at the signage of the first derivative. The second is looking at the second derivative. It's called the second order conditions, and it's about the concavity and convexity of the function. So let's start with number one. Now let's focus at the top. We're going to suppose that we have a function f of x, and it's differentiable, so it's not allowed to have any kinks, no places where the derivative does not exist, where it's not defined, on some interval that we're interested in. So on the interval that we're interested in. And this should say interval that includes c. Now we've got a diagram here. You can see looking at the diagram that clearly when x is equal to c, y is at its highest point. Nothing is higher on the y-axis with a greater value than f of c. If we are here, right, if we're some x below, then you can see right away that f of x1 is less than f of c if x1 is less than c. And over here, x2, we'll walk it over to the y-axis, f of x2, we have f of x2 is also less than f of c if x2 is greater than c. So whether we're to the left or whether we're to the right of c, we are going to be at a lower f of x. Make sure you don't forget the relationship between the derivative and the slope. If we're to the left of c, the slope is positive or 0. Right? It's 0. Looks like it's 0 right there. That's okay. The function is still increasing. Not strictly increasing, but it's increasing when we're to the left of c. And if we're to the right of c, if x is greater than c, then the slope is negative or 0. And in this case, it's strictly negative. If I draw those little tangent lines here, you can see that it's downward sloping. Similar situation, we're trying to evaluate whether d is a minimum. Clearly looking at the graph, it is a minimum. And we can see the opposite of the previous case. If f prime of x is less than or equal to 0 for x less than equal to c, and f prime of x is greater than or equal to 0 for x greater than or equal to c, then x is equal to c is a minimum point for the function f in the interval I. You can see here we've got the slope is increasing when x is greater than or equal to c. So that condition is satisfied. If I used c, but of course I changed it up a little bit and we're using d here. I better be consistent with this point d. If we're less than d, if x is less than d, the slope is decreasing, and the first condition is satisfied. So we know that point D is a minimum point for f on the interval or in the interval I. The second order conditions is our other test for determining if it's a maximum or minimum. This one is much more common in economics, so you need to know it. We'll work on it now, and we're going to see it again later when we look at local minimums and maximums. Looking at the graph, it should be fairly obvious that if C is a maximum, then the function in this area has to be concave. Right? What does it mean for a function to be concave? The slope is decreasing. The slope is decreasing. And you can see that it's positive here, and then it's negative there, and that's because the slope is decreasing. How do we write this? Well, if we've got a function defined on an interval, right, the function is f. Here we've got C is the critical point for f. What is a critical point? That's where f prime C is equal to 0. Right, the slope is 0. That's why we've got this horizontal line, that represents the tangent line, or it is the tangent line. It's a critical point for f in the interior of I, then if f is concave, then C is a maximum. Point for f in the interval I. Similarly, if we have a convex function, what is a convex function? It's one where the slope is increasing. It's going down there, and then when we get to the right of the point D, it's increasing. So as we get closer, moving from the left to the right, as we get closer to D, the slope is increasing. When we get to point D, the slope is equal to 0. And when we're to the right of point D, the slope is positive. And I can write if f is convex, then C is a minimum point for f in the interval I. Oops, I guess I don't need to write the interval. I'll just use I. Now we'll return to these tests again a little bit later when we look at local minimums and maximums. We'll actually do some examples together. Before we end the video, let's do an example together. Here's the function of interest. And whoa, a little bit of a typo there, but it's pretty clear what the question wants us to do. We're going to find the first derivative, and we're going to find the second derivative of the function g. And let's get started. So we know g prime of x is going to be equal to, well, 1 minus, well, we've got a 2 there. The 2 is going to stay. And I take the derivative of, or I take whatever is in the natural logarithm and put it in the denominator. And then the derivative of the inside would just be 1. So I'm just going to have a 1 there. And so g prime of x is equal to 1 minus 2 over x plus 1. What about the second derivative? Well, the 1 is just going to disappear. So that's going to be a 0. And then we've got a minus. I've got 2 over x plus 1. I could use the quotient rule, so I'm going to go ahead and use the quotient rule. So the derivative of the numerator is just 0 times the denominator, x plus 1, minus, and I got to make sure I don't make a sign error here. So it's the whole thing is going to be subtracted. And I've got a minus here. The derivative of the denominator is just 1 times 2. And I can close that bracket, but I also want to square the denominator here. And that's kind of messy, so I'm going to rewrite it again. And we've got 2 over x plus 1 squared. Whoops. Squared. There, that's a nicer to look at that way. So we want to find all extreme points. So that's question 1. So we did that and we're good. If I rewrite g of x, I haven't simplified it. I'm just going to keep it the way that it is, like that. Looking at question 2, we're trying to find all extreme points. And how do we find an interior extreme point? Well, we want to set g prime of x equal to 0. And so we get 0 is equal to 1 minus 2 over x plus 1. 1 is equal to negative, oops, that should be positive, 2 over x plus 1. That gives us x plus 1 is equal to 2, and x is going to be equal to 1. So x equals 1 is a critical point for f on the interval. Next, we're asked to sketch the graph. So let's take a look at the graph. Can we say something before we do that, can we say something about this critical point? Is this critical point going to be a maximum or a minimum? And we actually already know that it's going to be a minimum. And how do we know that? Well, looking at the second derivative here, this is strictly positive. Strictly positive for all x values, right? For any x, this thing is positive. Since it's strictly positive, we know that it's convex. So it's going to be convex. And I'm trying to write small because I'm running out of space. And it's convex generally, so we really know that this is going to be a minimum. Specifically at the point we're interested in, if I want to evaluate g double prime at our critical point, x is equal to 1, we find that we have 2 over 1 plus 1 squared, which is equal to 1/2, which is, of course, greater than 0. Since it's greater than 0, this function is convex, and the critical point we found is going to be a minimum. Now let's take a look at the graph and see if we're right. And we are. Yay. So we can see here that at 1, looks like we're at a minimum. I can draw a tangent line here, like so. And this thing actually is asymptotic around x equal to -1. It always has to be that x is greater than -1 because the logarithm of 0 has no solution. And it has no maximum. It just keeps getting bigger and bigger. And so the minimum value, or I should say the minimum point, is x equals 1. G is a convex function. Now, the question didn't ask us about that, but you can see here that this is clearly convex.